Good morning, everyone. How are you doing on this lovely Wednesday? Good to see you all here. Dorian, Serhi, and a couple people on YouTube. What's going on in your world today? Oh, it's a little bit cold here today. I didn't put on a sweater, but I can feel the cold breeze coming in through the window, and it's going to rain later today, so I'm kind of looking forward to that. But sunny right now, just a little bit chilly. Well, today we're beginning a new topic. I mean, it's still kind of related to graphs. This is a new kind of graph called a finite state machine. And I wanted to introduce this topic by playing a little game with you. So I'm going to need your cooperation. I'm going to need your input on this. There's a couple people on Zoom, and it'd be good if you could participate on this. So you can go ahead and just, if you want, just turn on your microphone and just shout out the answers, or you can post them in the chat. So pretend you're a pirate. You're trying to get to Treasure Island, and you're starting on an island called Pirates Island. And from every island that you go to, you can take one of two boats. You can take either boat A or boat B. And initially you don't know where the boats go, so we're just going to kind of explore around. So here we are on Pirates Island. Remember, we want to get to Treasure Island. And from here, should we take boat A or boat B and find out where it goes? Which boat should we take, A or B?
There's no difference between them right now? Just A or B?
Yeah, just pick one.
B.
I want to go to B. All right. So B is going to take us to Musket Hill, another island. Again, boat A or B?
Boat B.
I want to take boat B. That is going to take us to Mutineers Island.
B.
I'm going to do B. B from Mutineers Island. It's going to go to Dead Man's Island.
These names are getting progressively worse and worse. I'll stick with B, though.
B. This goes to Shipwreck Bay.
B
Okay,
again.
so
What would you say?
I was going to say, like, if we don't choose A at some point, we might not even be able to figure out what's going on.
So you want to pick A?
Sure.
All right. You end up on Musket Hill.
Did we just go in a circle?
Yeah, I think so.
Also, are there options where we don't end up on islands and where we end up in just open water?
No, no. Every boat. It's kind of like this is the pirates' equivalent of a bus system, right? So you take your boat and it goes from stop to stop, and no, you don't end up like being dumped out in the middle of the water. All right, where do we go from here?
Let's just go A from
A?
Musket Hill.
Oh, you end up back on Pirates Island.
Okay, so B.
B from Pirates Island?
Yep.
Back to Musket Hill.
And B again on Musket Hill.
B again. Takes you to Mutineers Island.
B on Mutineers.
Dead Man's Island.
B again.
Shipwreck Bay.
B again.
Dead Man's Island.
A on Dead Man's Island then?
A on Dead Man's Island. Oh, okay. Musket Hill.
What? B on Musket Hill.
Mutineers Island.
A on Mutineers.
A on Mutineers. Takes you to Smuggler's Cove.
Ooh, that's a new one. B on Smuggler's Cove.
Gets you to Treasure Island.
There we go.
Got it. Okay. So let's take us back to Pirates Island, and let's see if we can get to Treasure Island this time with not so many stops.
A.
Okay. A goes to Shipwreck Bay.
And A again on Shipwreck Bay.
Goes to Musket Hill.
Fine, hold on. B on Shipwreck Bay, because that one took us to Dead Man's, I think.
From Shipwreck Bay. So over here. B, yes, takes us to Dead Man's Island.
You go A on Dead Man's Island? I don't remember the path now.
Musket Hill. So instead of going to Dead Man's Island and then back to Musket Hill, you could have just taken boat A from Shipwreck Bay and gone straight to Musket Hill.
Also, isn't Musket Hill right next to what's it called? To Pirates Island? The original starting point.
Yes.
Go Pirates Island, Musket Bay, and then the next
Wait,
one after.
You want to start all over again?
Yeah.
All right. All right, so here we are. Start Pirates Island.
B from here.
Takes us to Musket Hill.
B from here.
Takes us to Mutineers Island.
A from here.
Smuggler's Cove.
B from here.
Treasure Island.
There we go.
So do you have a complete map?
Oh, not at all.
No? Have you? But you have been making a map.
In my head.
Oh, in your head. Well, that's not a very good pirate.
Not at all. But then the secret dies with me, so it's a win.
So you think that's the shortest route to get from Pirates Island to Treasure Island?
I don't think so, but that's the one that I found. That's the shortest route.
What pieces are you missing?
Rest of the map.
Like if you had been on Smuggler's Cove and you had taken boat A, that would have taken you all the way back to Pirates Island.
Okay, so then that's the complete map, I guess.
I think so. I think that's the piece you're missing.
I'm happy I went with B at the end.
Yeah.
If I went with A, it would have been
Kind of luck there.
pirate's luck.
So here's what the whole map would have looked like. This is the map that I'm following. So you start at Pirates Island, and I'll put a little arrow pointing at that, indicating this is where you start. And then, so on your map that you have in your head, where does boat A go?
Musket Hill. Wait, no. A or B?
A.
A goes to Smugglers or no. Something Bay, the one with the
Yes.
shipwreck.
Yeah, exactly. Shipwreck Bay. And where did
B
B
goes to Musket Hill.
B goes to Musket Hill. And then do you have anything from there?
Musket Hill goes to, I forgot the one with just a hill on it. I forgot.
Goes to another one that starts with M, I think.
Yeah.
Mutineer's Island.
The Mutineers
Yeah,
Island, yeah.
there you go.
And what boat did you take to get there?
I think it's B.
Mhm.
B, yeah.
And then from Mutineer's Island?
Take A, it's, what's it called? I forgot the one that's right before
Shipwreck?
the treasure.
Smuggler's Cove.
Oh, I mean
Smuggler's
Smuggler's Cove, yeah. Yeah.
And then
If you
finally,
take B, it's Dead Man's Island, I think.
from Mutineer's Island? Yeah.
If you take B from Dead Man's, it's to Shipwreck Bay.
Good.
A from Dead Man's was Musket Hill, right?
A from Dead Man's, yes, takes you back to Musket Hill.
A, yeah, A from Shipwreck Bay also took you back to Musket Hill, right?
Yes.
Doesn't it go both ways though? So if you take A from one spot, go somewhere, and then you take A from the other spot, does it go back to the same place?
No, not necessarily.
Okay.
Musket Hill, A is back to Pirates.
Mm-hmm.
Clearly, Treasure Island is at the end, but
And I'll put a double circle around that one, indicating this is our goal.
Smuggler's Cove goes back to Pirates as well
With boat A.
with boat A. Yeah.
Are we missing any? There should be an A and B coming out of every single one of them. We're missing, no?
We're missing B from Shipwreck Bay.
Ah, where'd that go?
I don't remember that one though.
I think it went to
That went back. It went back to Dead Man's Island. Okay,
it
so
would be better to make a map than keep it in my head.
so that's the complete map there. So this is called a finite state machine. And just to go over some terminology, those vertices are called states. So every time you make a transition from one vertex to another, you're changing your state. So these arrows are called transitions. The state that you start on is called the initial state, and it's indicated with an arrow pointing to it. And the state or states that you want to end up on are called accepting states. And there could be more than one. So if you look at this state diagram, you can see one of the paths to get you from the starting state to the accepting state, and that was to go Pirates Island to to Musket Hill to Mutineers, Smuggler's Cove, and then to Treasure Island. So one of the possible routes was B, B, A, B. What's another one that'll get you there?
A.
B, A?
A. And B.
Okay. So you had B, A, B, A, B. That one was a little circuitous, right? You ended up back at Pirates Island, but it got you there. What's another one? You could do maybe A, B, A, B.
Wait, wouldn't the second A be a B actually on that one?
What's that?
Oh wait,
I was doing A, and then this A here,
Oh, okay.
and then B, A, B. And then another one we could do is A, B, B. Oh, I see what you're saying. I see what you're saying. This should have been a B here, right? This was a B.
I think so. Yeah, I was trying to.
Yeah.
Okay. Yeah.
A, B, A, B, A, B. Would ABA work? A, B. Oh, I see. You were just making the correction for that one that had 3 A's.
Yeah. Just that second.
Right.
Yeah.
What about B, 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 A, B, A, B?
Yeah.
So is there an infinite number of paths from the start to the accepting?
I don't think so.
Well, the fact that there's a loop in here, the fact
You
that
mean if you can just keep taking the
just,
same pathway?
Yep, you can just loop,
Oh.
loop.
Then
Right?
yeah.
Right. So yeah, there's an infinite number of possible ways to get from the start to the accepting. So each one of these paths is called a string. You can see they're kind of related to the strings you're used to from your programming languages, and they're constructed of a sequence of characters. And the set of all acceptable strings is called a language. So the set of all these strings that get you from the start to an accepting is called the language for this particular finite state machine. So for this finite state machine, there's a set of possible symbols, and there's only 2. There's A and B, and you can construct strings out of those, and the strings form, all the strings that you can use form what's called the language. You probably noticed that all of the strings in this particular language end with BAB. So there can be a variety of other characters coming before, but the very last thing has to be BAB. So let's take a look at some other finite state machines, and let's write down the language for each one of these. So what are all the strings that finite state machine number 1 can accept? There's only 2, but what are they?
You can have AB and AC.
Good. AB or AC. What about for number 2?
B, AB,
Say that again.
B or AB.
Good. B or AB. And then number 3.
Y is definitely one of them.
So you could do just Y. That'll take you from the start to the accepting. What's another one?
XX.
XX, good.
I'm a little confused on if you can go from your goal to another goal. Does that work or
That's
no?
fine, yeah. So if you take, like, say, Y and then do X. So the goal is just to end up on one of the acceptings. Doesn't matter which one. And you can pass through one of the acceptings as well.
I don't know what to do with those loops though, because if you just go, technically they're infinite. You can add as many Y options as you want.
Yeah. So you could do like X and then a whole bunch of Ys and then an X and be done.
You do 3 X's.
1, 2, 3, yeah. You could even do 3 X's followed by a bunch of Ys.
You can do anything on this, right? It involves X and Y's.
Is it absolutely anything?
Almost.
Like, you can't just do a single X.
Yeah.
That one doesn't
after
work.
Yeah.
So it's not any mixture of X's and Y's. It's a specific mixture. Nevertheless, this is another infinite set of strings, isn't it?
Yeah.
The fact that
You
there's
always have to start out with either an X followed by something or a Y. You can't just have X. That's the one limiting factor of the whole thing.
But, can it be any mixture of X's and Y's? Are there any other strings that don't work?
I don't think so. I can't really see any.
How about X, X, Y?
No.
So
Yeah,
X,
you're
X,
not gonna
Y does
stop
not
on-
work. So there are some strings that don't work. But there are a lot of strings that do work. And Akash on YouTube says, X followed by any number of Y's never works. That's true. A single X followed by any number of Y's never gets you to an accepting state. What about number 4?
Nothing gets you to your accepting state.
Good. So one of the possible strings is what's called the empty string, which we represent with the Greek letter epsilon. This means the empty string. In a programming language like C or Java or Python, you would represent the empty string with just 2 quote marks. It's a string with nothing in it. What else works?
XYX.
Good. X, Y, X. Anything else?
I think it just has to be an infinite repeating loop of XYX, because if it's not anything else, it'll land on a bad state.
Can you do an empty string and then XYX?
So it's basically an empty string or any number of XYXs.
Or can you do both of those things?
How do you mean?
Like an empty string and then concatenate XYX.
Oh, yeah. I see what you're saying. So, well, it's one or the other, right? It's either the empty string. Well, I guess you could say it could be like the empty string followed by XYX, right? Like that. And,
Yeah.
you know, that works too, because again, in a language like Java or Python, if you said something like quote, 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 plus, quote, hello, right? That's really the same as just hello, right? You're concatenating an empty string onto an existing string, and it doesn't really do anything. So when you're constructing finite state machines, there's basically three constructs, three pieces. You can string the states along in a line, and that's called concatenation. You can have the states with two or more alternative directions that you can go. And you can either go off in two separate directions, or you can make two directions that just end up at the same state, but still you're providing some alternatives. So we call this alternation. And then finally we've got repetition, which is formed with loops. You can either go back to the same state, or you can maybe make a string of states that loop back and forth. And so you might recognize these as being the basic building blocks for any programming language. You've got sequencing, which is just a list statements one after another. You've got if, else, or some kind of conditional, and you've got loops. And pretty much any programming language that has these three things is a complete programming language that can do anything. And so what this means is that with finite state machines, you can construct a finite state machine to represent all the possible programs that you could write in a particular programming language. But you're right. Finite state machine. So being a complete programming language is my sort of layman's term for what's called Turing complete, which is a programming language that can basically do the same thing that any other programming language can do. But finite state machines themselves are not Turing complete, and we'll get a chance more to talk about that later on. Okay, so let's go over some more finite state machines using those three building blocks. I've got 5 of them on the screen here. And we're not only going to talk about what is the language that these finite state machines accept, but also what are called regular expressions, which is a way to represent the language that a finite state machine accepts, but using symbols rather than diagrams. So obviously, for the first one, the language is just AB. There's only one string that it accepts. And the regular expression that represents that language is just AB. For number 2, this one accepts A or B. So we write that using a vertical bar, which means or down here. So what are the two strings accepted by number 3? And what do you think its regular expression is?
So ABD or ACD, and then with a
Good.
line in between those two.
ABD or ACD. And so we could write that as ABD or ACD. We could also just compress that a little bit as A followed by B or C followed by D. So we can use the parentheses to group smaller regular expressions together. How about number 4?
A
Good. We could do AA.
or A with an infinite number of B's. A.
Good. So for a regular expression, we can represent that as A followed by any number of B's followed by an A. So here the star is being used to modify the letter right in front of it. And the star means basically a loop, or 0 or more of those things. And then finally, number 5.
A, B with an infinite number of B's. And then I think that's an A. I don't know.
So
Yeah.
A,
A.
A, B, and then we could just do A at that point, right? And we could also do A, B, B, A, and A, B, 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 A. So it's got to have at least one B. So the regular expression for this would be A, B, and then any number of B's followed by an A. Now, some of you have seen regular expressions before. If you've taken the Unix or Linux class, you've probably used regular expressions in some of the pattern matching commands like grep and awk and sed. If you've done programming in, what would be a good one? Like you've done PHP programming for the web, you've probably also used regular expressions before. And you may be familiar with regular expressions that use more symbols like plus and question mark and things like that. So what I'm showing you here with the vertical bar and the star and the parentheses are called basic regular expressions. These are the only things that you need to be able to construct any regular expression. The ones that you may have seen in programming languages have some additional symbols, but they can all be broken down to these 3 basic ones here. So all the other ones you've seen, like plus and the curly braces and the question mark, are really just shortcuts for combinations of the ones that you see here. So at this point, we're sticking with just these 3 symbols, the vertical bar, the star, and the parentheses, and then we can construct any regular expression from that. So the other ones you've seen are just kind of shortcuts for combinations of these 3 that you see on the screen. So here's another one. What's the language of this finite state machine? And how about a regular expression for it?
I think the expression would be A and then in parentheses B with a star, C with a star, and then a D on the outside of the parentheses.
So, like this. Is that what you said?
Yeah, I think so. I think so. Yeah.
You think so? Well, let's write down some of the strings that this finite state machine accepts and see if it kind of matches what you've got there. So I can see here the one possible string is just AD. That's the short one that goes straight across. What's another one?
ABD
Good. ABD.
and ACD.
Mm-hmm. ACD. What else?
ABCD.
ABCD. Good. How about ACBD?
Mm-hmm.
How about ABBBCCD? Can you mix up the B's and C's? Every time you come back to this state, you can make another decision about what direction to go in. So I can do A, B, and then a C, and then a B, and then a C, and then a D. So I can mix up those B's and C's. I could do A, B, B, C, B, B, C, B, D. So of course there's an infinite number of them because we have a loop. So what do you think about this regular expression that you came up with? So this regular expression certainly means you have to do an A, which is great. You've got that one covered. And then inside the parentheses, you've got any number of B's followed by any number of C's. So inside the parentheses here, you're suggesting that there's an order in which they have to come. First the B's, then the C's, followed by a D. So this regular expression does not allow, for example, this string right here. Because you have to do all of your B's, and then you can do all of your C's, and then you can't go back and do any more B's. Because you've got a sequence here. You've got a sequence of B's followed by C's. So this one is not going to work. Let's try again. So we need to incorporate into the regular expression the fact that there's a choice that you can make. You can either go this way or you can go this way. Now, a couple of people in the chat have suggested A, B star, C star, D without the parentheses. But this one has the same problem that the first one had, in that you have to do an A followed by any number of B's, followed by any number of C's, and then followed by a D. So this is not going to work either. And then a couple more people suggested this one. And this one actually works well. This is not the only one that you can do, but this one works well. So you've got an A followed by either a B or a C, and then repeat that any number of times. So here the star is modifying this whole thing. You can repeat the B or C as many times as you want. Every time you come back and do the loop, you can make that choice again. So you've got a B or a C, and you can keep repeating that. So once you make the choice, you don't have to repeat that particular choice an infinite number of times. You can come back and make the choice again. See the subtle difference there? So as you loop around, you can make the new choice, B or C, and then you loop around, make the new choice, B or C. So this one works. But can you think of another one that would also work? This one here is a little weird, but it looks like this. So this is kind of similar to the first one you suggested, but I'm going to put a star on the end. So this one here still has the star, which modifies this whole sub expression, but then you can do any number of B's followed by any number of C's, and then go back and loop that again. So you could do like 3 B's and a C, and then go back and do that repetition again. You could do no B's and then a bunch of C's, and then you could do a bunch of B's and no C's. So this will work as well. It's just a little weirder than I think this one up here, which is a little more straightforward. And then another suggestion here was A, and then B star or C star, and then a star out there. That'll work as well. So you may be wondering at this point, is there an order of operations for these ors and stars and parentheses? And yes, there is. So I might want to point out that A, B, or C, D is not the same as A, B, or C, D. So when you're doing order of operations, of course, parentheses comes first. And you can kind of think of the star as being equivalent to exponent in arithmetic. You can kind of think of concatenation as being like multiply. And alternation as being kind of like add. And if you remember, several weeks ago, I mentioned that there was kind of an equivalency between the different symbols that we use and the different branches of mathematics and the order of operations. That we've got grouping, we've got exponent, we got multiply, and we have adding. Okay, and the reason why these are not equivalent is because this top regular expression accepts A, B, or C, D. There's only 2 strings that it accepts, A, B, or C, D. And the bottom one here accepts A followed by B, or C followed by D. It also accepts 2 strings, but they're different strings. This one accepts A, B, D, and A, C, D. And this one up here only accepts AB or CD. And the reason for that is that the alternation, the bar, is the lowest precedence. And so we've got basically a left or a right-hand side. Now, if you recall back on Monday, we started talking about the phases of compilation. That you got your source code, it goes through a tokenizer or a lexer, and then from there it goes into a parser, semantic analysis, code generation, code optimization, and then finally your target language. So let's focus on that first box, that tokenizer or lexer. This is a program that takes your source code and goes through all of the characters in your program, groups them into what are called tokens, and then labels each one of those tokens with what that thing is, whether it's an integer or a variable or a keyword. So if we have an expression like, or a statement I should say, like BC equals x plus 3 times age, we need to go through and tag each one of those pieces with what they are. After the tokenizer is done, you get this token stream, which consists of the source code with these tags attached to each one of the pieces. Like BC is an identifier, and X is also an identifier, and 3 is an integer, and age is an identifier. And we've got the multiplication, addition, and assignment operators. So how does the tokenizer do this? Well, it does it with regular expressions and finite state machines. We can write down rules for what something like an integer is. So let's think about that for a moment. What does an integer look like? And you need to divorce yourself from thinking about an integer as being a number, and instead think about it as being a sequence of symbols. What symbols do we use to represent an integer, and what are the rules for organizing them into strings that look like integers? So you might start out by thinking, well, what are some valid integers that I would accept in my program? Obviously, I'd accept something like 3, 167, 2022. Those are the easy ones. But what are some integers kind of like, on the borderline between acceptable and not acceptable? Would I accept negative 86? I would say, sure, that's probably an integer. What about 0? Should I accept 0?
Yeah.
I would say, sure. What about 2 zeros? Would I accept that?
Yep.
Yeah? Now, we might not normally think of that as being an integer. If somebody said, I caught 0 fish today. We'd say that's a little weird, but is it acceptable as an integer? In other words, if I type that into a program, should the compiler reject that as being not a number, or should it accept it? Now, I think most people would say, sure, from a programming language point of view, that's probably acceptable. What about 007? Is that acceptable?
Of course.
Yeah. How about negative 0? Will that work?
Yeah? Can you have a negative 0? Weird.
It's weird, but does it compile?
Probably. I don't know.
So you as a language designer get to decide, would I accept this as being an integer, or should I reject it as being an error? I'm not saying that there's a correct answer, because there isn't a correct answer. Is that you as a language designer get to decide, will I accept integers that begin with a 0? And likewise, what if I put a plus in front? Is that an integer? So given that, let's see if we can write down some rules for what an integer looks like. So if we allow all of these things and say all of those represent valid integers, then we can tackle things like the obvious cases first, right? So an integer could be as simple as a single digit, or it can have multiple digits, but obviously it has to have at least one digit. And the first digit could be anything. Now, if we disallow integers to begin with 0, we'd have to say the first digit must be the numbers or the symbols 1 through 9, but then that would disallow 0 by itself. So we'd have to kind of make a special case for that. So we could say 0 or 1 or 2 or 3 or 4, right, or 9, followed by 0 or 1 or 2 or 3 up to 9, and then any number of those. So we've got a starting digit, one of the 10 possible digits, followed by any number of digits subsequently. And that handles the easy cases. That handles, like, you know, all of these and all of these. It doesn't handle the ones with the symbols in front, the plus and the minus. So that's fairly easy to do. I'm just going to move this over a bit. And we can say a dash or a plus or nothing. So an integer is a minus or a plus or nothing, followed by a starting digit, followed by subsequent digits. And using just the symbols we've learned so far in basic regular expressions, this is what a regular expression for an integer might look like. Now, from a programmer's point of view, this is kind of tedious to type in. And so most programming languages have an additional set of symbols for doing ranges of characters like we've got here, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We can do it like this. We could do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means any one symbol out of that set of symbols. So it means you just don't have to type all those vertical bars in between them. And then they have a further optimization that lets you do a range of characters. And this is nice and compact. So you do it like this. Dash or plus or nothing, right there. Followed by a digit, followed by 0 or more subsequent digits. Okay, but if you wanted to disallow zeros on the front, if you wanted to disallow things like this, but also allow just a single 0, you could do that as well. You could do minus or plus or nothing. And then you could do 1-9 followed by 0-9 star. Or just a 0. So what that would allow is numbers that started with a non-zero and had an optional plus or minus in front, or it could be just a 0. So this would disallow -0, and it would disallow these funny ones that had multiple zeros on the front. What about identifiers? So for identifiers, it's almost the same as integers, except that we're using letters instead of digits. So you've got, A or B or C or D, up to Z, followed by A or B or C, up to Z star, which of course you could shorten into A dash Z, A dash Z, star. But these are the kinds of regular expressions that the tokenizer or lexer uses to figure out what each one of those pieces are. Is it applies these patterns to your program, and as the patterns get matched, it then tags each one of those things that matches with what it is. And if there's a piece of your program that doesn't match the pattern, then it flags it and it says, this is not something I recognize. So basically, it starts here from the beginning of the string or the beginning of the program. And this is why it's called a scanner, because it's scanning from left to right. And it is successively trying to apply these patterns to it. It might try this one first, you know, and apply this pattern to it. And start going through here and go, oh, that doesn't match. Let me try this one. And it goes, oh, that does match. So this must be an identifier. And then it keeps scanning from there. And of course, we would have a pattern for matching things like the equal sign. So that will get flagged and it says that's an assignment operator. Then it keeps scanning and it goes, oh, that is an identifier. Here's the plus. Here's an integer. Here's the times. Here's an identifier. And then here's the semicolon. So it just works from left to right, tagging each one of the things as it goes, as it's applying the patterns. So basically, whatever is the longest pattern that matches is what it gets flagged as. How does it tell the difference between keywords like if and while and things like identifiers? Well, it checks those keywords first. So it looks for words like if and while and for and repeat. It looks for those things first. And then if it doesn't match those, then it goes on and tries the other rules for things like identifiers. And so that's how it doesn't confuse the keywords with identifiers. Okay, so that's how that tokenizer works. It's really just a whole bunch of regular expressions that you type into your language specifier, and then it just applies those patterns to your program, and then whatever pattern matches, that's how it knows what that thing is. Why did old languages use semicolon at the line of the code? That's so it could tell the difference between the end of one statement and the beginning of another statement. So most languages have some kind of statement terminator. C and Java obviously use the semicolon. Python just uses the enter key as the statement terminator. And there was an old language called Pascal that required that the very last character of your program be a period. So you had semicolons separating all the statements, and then you had a period at the very end. So it was almost like writing out a list of things, like almost like a to-do list, right? You have to do item A, semicolon, item B, semicolon, item C, semicolon, item D, period. And that period was mandatory. You had to put that period there, or it didn't work. So it basically said a program consists of a sequence of statements. Each statement ends with a semicolon, except for the last statement. The last statement could not end with a semicolon. It had to end with a period. So as far as implementing a state machine, it's actually very easy to do in any programming language. All you need to do is have a variable that keeps track of what state you're in, and you could use just something like an integer, and then a whole sequence of if-else statements, and it looks like this. So if this is your state machine, if this is the state machine diagram that you've written out or drawn out, then here's what the entire program would look like that implements that state machine. We've got a variable that represents what state we're in, either 1, 2, or 3. And then a loop that goes over your input string. It just loops character by character from left to right. So if our input string is, let's say, A, C, B. Then a symbol will be an A first, and then it checks to see if I'm in state number 1 and the symbol that I just read in is an A, then move me to state number 2. If I was in state number 2 and my symbol was B, move me to state number 3. And if I was in state number 2 and my symbol was C, then stay in state number 2. Anything else would be an error, basically. And then finally, after we're done with that loop, after we loop through all of the symbols in my input string, then we check to see what state we're in. If my state was 3, then great. I succeeded. Otherwise, I failed. So that's what an implementation of a state machine looks like. It's just a variable to keep track of what state you're in, and then a loop that goes over all of your symbols in your input, and then just changes the state as it goes along. So state machines actually get used in a whole bunch of different applications, not just in pattern matching. Think about something like a video game like Mario, Super Mario. You've got a state that might represent what level you're currently on, and you move through the game as the level progresses. And you've got other state machines that represent things like how big is Mario and how fast can he move, and what power-ups he's collected so far. And each one of those states affects the gameplay. And you can move from state to state. As you collect a power-up, you can change size. That's part of your state. As you get to the end of a level, you move to the next state, which represents the next level that you're on. And so if you organize your program in that fashion with variables that keep track of what state you're in, and then conditions that move you from state to state, it's actually, in some cases, very easy to construct what seems like a very complex program and just boil it down to a whole bunch of states. Now, if your programming language supports a data structure, which in Python is called a dictionary, or in Java is called a hash map, or in JavaScript, which is called an associative array, then you can actually simplify this a little bit. You might see that we can build a data structure to represent this finite state machine. On the left-hand side, we could write down a pair of values representing what state you're in and what symbol you just read. So if we're in state number 1 and we just read in an A, then our new state is 2. And if we're in state number 2 and we just read in a B, our new state is 3. And if we are in state number 2 and we just read in a C, then our new state is number 2. And so this data structure or dictionary captures all of the information that's in that finite state machine as far as the transitions go. And then my program to execute this really becomes quite simple. I still have initializing the state to 1, and then I say for symbol in my string, state equals, and let's say I will call this whole data structure, I'll call this FSM, finite state machine. So I just do a lookup into this table. I plug in the state and the symbol. That goes in to the left-hand column, and whatever value matches, I pull out the right-hand column, and that becomes my new state. And that's the whole loop. And then finally, if state is equal to 3, then success. So rather than a whole bunch of if-else statements to evaluate what state and symbol you just read in, you just use a dictionary, a data structure, to hold that information. And now you've got a really compact, easy to program engine that can execute pretty much any state machine. You just build that data structure that contains the information about the state machine, about the transitions, and then you initialize your state. You run this loop that just successively plugs in values into your state variable, and then what comes out the other end is your is what state you ended up on, and then you just check to see if you are in one of the accepting states. Really easy to do. Okay, and so what that means, and this is kind of like one of the big picture concepts here, is that every finite state machine that you can draw can be implemented as a computer program. Doesn't matter how complex that finite state machine is, you can represent it with a computer program. You can either do it with a whole bunch of if-else's, or you can do it with a data structure and then a tight little loop. Also, every regular expression can be implemented as a finite state machine. And the opposite of that is also true. Or I should say the inverse of that is also true. Every finite state machine can be represented as a regular expression. And so what that means is that regular expressions and finite state machines are what are called duals. They're absolutely equivalent to each other. You can transform one into the other and back again. Any regular expression can be turned into a finite state machine. Any finite state machine can be turned into a regular expression. There's no exception to that. There's no language that some regular expression can accept that some finite state machine can't accept. And there's no language that some finite machine can accept that some regular expression can't accept. They both accept the same kinds of strings. If you can write a finite state machine for a particular language, you can construct a regular expression for that language. And since every finite state machine can be represented as a computer program, so can every regular expression. Okay, so that's kind of like the big picture concept here, is that finite state machines and regular expressions are just two ways of representing the same thing, a way to capture strings that can be accepted by either a finite state machine or a regular expression. Now, there's some chat going on here that says that finite state machines aren't Turing complete, that finite state machines themselves aren't complete programming languages, and that's true. You can use a regular expression to represent a programming language, but it itself can't execute the same kind of programs that a programming language can. And the reason for that is that finite state machines and regular expressions, of course, don't have any kind of memory. Regular expressions cannot remember what has happened in the past. For example, there is no way to construct a regular expression or a finite state machine that can do things like match parentheses. Like for every opening parentheses, there's a matching closing one, and that they're nested properly. Finite state machines can't do that because they have no memory about what has happened in the past. They can't count how many opening parentheses there are and then match that up with an equivalent number of closing parentheses because there's no memory involved. You could construct one that could count a precise number. I could say, like, I could construct a finite state machine that could make sure that there's, for 3 opening parentheses, there are exactly 3 closing parentheses, because I could just use a state to represent every time I see an opening one, I can move to a new state. And every time I see a closing one, I just move back. And so if I end up back on my starting state, then I know I've got a matching number of parentheses, but it only works for a concrete number of parentheses. I can't do it for an unknown arbitrary number. So there are different kinds, and this is kind of extra stuff here. There are different kinds of finite state machines. There's two other kinds that are not important for this course, for this introductory course for discrete structures. If you go on to a a 4-year university where you take a course in programming language theory, then you'll probably be, hopefully you'll be exposed to the other two kinds. So we've learned here about finite state machines, and there's also one called push-down automatons, PDAs, and that's where you can add, it's still a finite state machine, but your state is not just a single variable, it's now a stack where you can push values onto it and pop values off to it. That essentially gives you a little bit of a memory. It's kind of like having a register in your processor that can hold a value. And now you can do things like match parentheses, right? Every time you see an opening parentheses, you push a value onto the stack. And every time you see a closing parentheses, you pop a value off the stack. And if you get to the end of your string and your stack is empty, then you know that you've got an equivalent number of opening and closing parentheses. So now you can do things like matching parentheses. But a push-down automaton still can't do everything that a programming language can. And so there's a third kind called a Turing machine, which is a push-down automaton. So it's got a finite state machine with a stack, and it also has essentially a memory, which is represented as a long string of, you can think of it as being like a paper tape, like from a calculator or a cash register. And it's broken up into cells, and you've got a read-write head that basically can move along that tape and can read and write values in and out of that tape. You can put one symbol in each cell. You can you can write a symbol to it, you can read the symbol from it, or you can replace the symbol. And that essentially gives you now a working computer. It's a slow computer, right? But it has loops, it has a memory, it has conditionals, it has all the pieces of a computer. It's just a abstract mathematical model of a computer, but you probably heard this term like Turing complete. And what that means is that a particular programming language can do everything that a Turing machine can do. And a Turing machine can do loops, it can do conditionals, it can do subroutine calls, it has a memory, so it has all the pieces of a modern computer. And so any programming language that is described as being Turing complete means that it can do basically anything that any other Turing complete programming language can do. And so kind of the big picture out of that, and what you get out of a programming language theory course, is that you have all these programming languages out there like Python and Java and JavaScript and PHP and Perl and Scheme and Lisp. And ultimately, they're all equivalent to each other. There's nothing that one programming language can do that other programming languages can't do. And sure, you might say, well, Prolog can't do web pages. Well, that's true, but that has nothing to do with the language itself. It has to do with the libraries that came with it. You could get Prolog to do web pages. It's just painful, but it'll work eventually. So again, that's for an upper division programming languages theory class, not for this lower division stuff. Nevertheless, it's something to look forward to, that you'll learn more about what is and isn't computable. And one of the other things you'll learn in that language is that there are actually some things that can never be computed. There are some problems that can never be solved by any program, which is kind of an interesting thing to think about. There are some things out there which you could never, ever write a program for. And it's related to this idea of, well, we have debuggers, right? Debuggers and debuggers can't actually remove the bugs from your program. All they can do is help you find them. Why can't we write a debugger that can actually fix programs? That's related to that problem of what are some things that are computable and what are not. And the reason why we can't have a debugger that can actually remove bugs from your program is because it's one of the things that we can't solve. Anyway, I think we're basically done for today. I don't have a programming assignment for you, or an assignment for you to do this week, because we're not quite ready for it yet. We'll do that next week. After we get a little more experience with regular expressions and finite state machines, then we'll move on to the last programming assignment of the semester. And we'll do that next week. So what that means is that we've basically reached the end of today. So I guess I should ask, do you have any questions?
With the debugger thing that you mentioned, it can find the bugs perfectly fine, but it can't like edit the code itself, or what's the problem there?
No, there are some bugs that no debugger would ever be able to find.
But a human can find them.
Perhaps. And for simple programs, this is easy to do. What we're talking about is if I threw an arbitrarily complex program at this debugger, would it be able to figure out if the program behaves correctly in all cases, or if there are some cases in which it doesn't behave correctly?
Oh, I understand. So it's like it would have to go and test every possible case at random, but being that computers aren't really that random, you couldn't test everything on it.
Yeah, because there's essentially, one way to think about it would be there's an infinite number of possible inputs. And so there's no way to try them all.
Get close to it if you have like
You could get close, right?
trying, but you can't
But
actually.
you could never do them all.
Kind of like in video games, how like some games will be shipped, um, like complete in quotes, but realistically, there's still tons of bugs that the programmers haven't found because they haven't tried it enough. But once it gets shipped out, there's thousands and hundreds of people trying that one specific part of the game,
Yeah.
and one of them might come across a bug, or it could be done
Yeah.
with programs as well.
If you're interested in researching this is called the halting problem. And there's some videos on YouTube about how the halting problem was determined that no computer could ever solve that problem. And since there's at least one problem that computers can't solve, that means that we can't say that computers can solve every problem. There's at least one that it can't. There's others as well, but that's one of them. And so it was a very interesting proof that was done. I don't remember when it was done, but in the past 100 years or so. And they were thinking about, is it possible that computers are the be-all, end-all, that they compute every possible question you come up with? And then it turns out there's at least one that it can't. Which means there's no way to have a computer find every bug in a program, because there's at least one that it can't find. And Abdul on YouTube is pointing out this is what's called a runtime bug. It's a bug that would only show up when you ran the program. And so the question here, to give you a little teaser, is, since this is a runtime bug, a bug that only shows up when you're running the program, it's not possible to write a debugger that can analyze the program before you ran it and determine if that bug exists.
Try a debugger that checks while you're running it. Then that wouldn't be a debugger.
No.
That would be
Right.
that would just be a program.
Right. So the question is there a way to analyze a program and determine if that bug exists without actually running the program?
Because you would have to. Yeah, that's a weird thing to think
It is a
about.
very weird thing to think about. But the fact that it was proved that there is a certain class of problems that no computer can ever solve means that we don't have to waste our time trying to do that. So again, if you're interested, go look up the halting problem on YouTube. Let's see if I can find something very quickly.
I found a few videos.
Yeah, there's one by Computer File and Lydia. Oh, that there's one by UDI Productions, which does some really cute animations. I was doing that in my other course yesterday. I was showing some videos from that channel.
Looks like I have some videos to watch while I'm eating lunch. Tom Scott, of all people, has one.
Oh yeah, so you know that's going to be a high quality video there, involving some dry humor.
His videos are really good,
Yeah.
really well done.
I don't know. We got some time. Let's just throw it in there and see what happens. Should we do Tom Scott's?
This might have copyright infringement all over it.
Maybe. Oh, maybe we'll do the one by UDI Productions. I know that one works. Got to get past the ad first. Give me a moment.
This is Computing Machine A. A solves problems in arithmetic. It receives a problem written on paper, and it prints the answer. It always prints the right answer. Here's another computing machine, C. C plays checkers. It receives the current state of the board, and it prints how it would move one of the red pieces. C plays checkers so well, it will never lose a game. A and C are machines we can already build today, and computers keep getting smarter and smarter, so will they eventually be able to do everything? Let's feed A with a board of checkers. A was not designed to handle this kind of input, and when it tries to process it, it gets stuck. The same thing happens to C when fed with a question in arithmetic. Let's draw a blueprint of A. This blueprint is detailed down to the level of the logic circuits, and it fully defines how A works. We are now finally ready to introduce a marvelous machine called H. H solves what is known as the halting problem. It can analyze the blueprint of another machine and determine which inputs are good for it and which will cause it to get stuck. It receives the blueprint of the machine to be tested and an input to test it with. Based on the blueprint, H simulates the given machine on the given input, and then determines if it gets stuck or not. H solves the halting problem perfectly. It always prints the right answer. Here are two more examples with the blueprint of the checkers machine. H is a nice machine, but can we really build it? We'll now prove that its very existence is logically impossible. Let's assume that H does exist. We'll place it on this stand for reasons that will be made clear in a minute. Recall that we assume H solves the halting problem perfectly. It should always print the correct answer. We are about to put this to the test. This is a photocopying machine. It simply prints 2 copies of its input. We'll place it behind H. Here's another simple machine. We call this one the negator. When the negator receives the words "not stuck," it gets stuck. And when it receives the words "stuck," it does not get stuck. And it prints a smile. We'll place it in front of H. Let's wrap it all in a neat package we call the X machine. X has 1 input and 1 output. Let's draw its blueprint. As before, this blueprint fully defines X. What do you think will happen if we feed X with its own blueprint? Will it get stuck? Let's find out. P simply duplicates our input. H receives 2 copies of the blueprint of X. It should now determine what happens when X is fed with its own blueprint. Let's assume it says, "not stuck." N negates that and gets stuck. So feeding X with its own blueprint causes it to get stuck. But H said it wouldn't. H was wrong. Let's try again. This time, we'll assume H says, "stuck." X didn't get stuck. But H said it would. H was wrong again. But H is supposed to always be right. This is a contradiction, proving H cannot exist.
So there you go. Some problems cannot be computed. Or I should say, there's at least one that can't be computed. I remember doing the halting problem in my programming language theory course, and just my head just like exploding at this idea. Well, not the idea, but the proof itself just seemed like, it's a proof by contradiction. What? So we have to like, how does that work again? I guess it works. I mean, it seems to.
It's weird because you put like the one thing that stops X from working is the little machine at the end that says it's stuck or not stuck. So it's just always disproving itself, which is weird.
Right. So basically, the halting problem solver will get stuck if it doesn't get stuck, and it won't get stuck if it does get stuck. But the fact that you were able to construct a program that doesn't work in all cases means that there's some programs that don't work. But that video really makes it easy to understand how that theorem works. So when you get time, go watch the one by Tom Scott and the one by Computer File.
We'll definitely do that.
Yeah. All right. Well, I think we've reached the end of today. Again, we'll have the programming assignment about regular expressions coming up next week. So you get a week off this week. If you have some assignments that you haven't yet completed, now would be a good time to go through and just make sure that everything has been completed. There have been some assignments you probably turned in that I haven't gone through yet and marked complete. So just, again, just make sure that it has been turned in. If it hasn't been marked complete yet, then I just haven't gotten around to it yet. So I hope that you have a good day. I hope that you got something out of this lesson. And we will continue with finite state machines over the next couple of weeks. What we're going to be focusing on is how does the computer actually start with a regular expression and turn that into a computer program. If you remember about 10 minutes ago, I said every finite state machine can be turned into a computer program, and every regular expression can be turned into a finite state machine, and vice versa. So how does the computer actually do that? How do you type in a regular expression, and how does it turn that into a finite state machine engine that you saw on the screen about 10 minutes ago? And that's what we're going to be learning about over the next couple of weeks, are the steps that the computer goes through to make that happen. So essentially, we're going to learn how a regular expression compiler works. A regular expression is itself a little language. It has a grammar. It has symbols that are used. So it itself is a little tiny language. It's not a Turing complete language, so it can't do what Java or Python can do, but it is itself a little language, and we'll learn how that language is itself compiled, essentially, into a finite state machine, and therefore turned into a computer program. So that, again, will be the next couple of weeks. And then after that, we'll have about a week or so, week and a half, where I have kind of nothing scheduled. And then we'll be able to do just some extra stuff. We'll just be able to have fun on those days. I'm thinking we might do one session about quantum computing. You've probably heard about that. And so I think once you learn about state machines, then some of the stuff in quantum computing makes some more sense. So we'll get through that first, and then we'll talk about quantum computing. I may do a day where I show you how some of these old computers back behind me are actually programmed. Like, how did we write programs back in the 80s and 90s on these old computers? And then who knows what else? We got another day or so of other stuff we could do. Okay. So yeah, have a great day, and I will see you all next week.
See you later, Professor.
Right. Bye-bye.
Bye.
And then, yes, tomorrow's class is, I'm responding to Akash here. Tomorrow's class is the C one. And in that one, we will be continuing with how to sort and search an array of structures so that we can crack these hashes really fast. And if you came in a little late on today's session, then yeah, go back and rewatch the video and you'll be able to catch up on the stuff we did. Right, so just to review, Mondays and Wednesdays I have this course, the Discrete Structures course, and on Tuesdays and Thursdays I have my C programming course. And in that one we are doing what we did in this one a few weeks ago, which was cracking passwords, but we're writing programs to do it. And to be able to do that, we have to build data structures that allows us to search the data structure really quickly to find the hash we're looking for, and then print out the corresponding password. Oh gosh, could we make it a linear order? No, a linear constant time operation by hashing the hashes. You know, I suppose we could. That would be, well, then we wouldn't be able to use the nice binary search function that comes built into the language. You're still going to find out. It's really fast. Really, really fast. Oh, which semester are these courses in? I see what you're asking now. So these are not introductory courses that someone in their first semester would take. It's something that they would take in their second semester, maybe even their third semester. Actually, discrete structures, a lot of them wait until their fourth semester, the end of their second year, to take this course. But really, it's for anyone who's taken at least an introductory course should be able to take it. So someone is to be taking second or third semester, which will be end of the first year or beginning of the second year. Some universities save this material for upper division. So we do it here at the lower division in the first 2 years because that's what our primary transfer institution. Most of our students come to our college and are just here for 2 years. And then they transfer over to a 4-year institution. So instead of starting their 4-year college career, if you can call it, at that 4-year institution, they start with us. And the advantage of starting with us is we have much smaller class sizes. So our classes are typically only about 30 to 40 students, whereas at a university, they could be 100 to 200 students. So you get much more like contact with your professors and the more ability to work closely with them to get questions answered and so forth. Also, the community colleges here in the United States tend to be a bit cheaper. You'll get basically the same education, but we're like not a tenth, maybe a fourth the cost of a 4-year institution. And that may be strange to some of you. I mean, you probably live in countries where your 4-year college educations are always free, but here in the United States, they're not. So students usually will pay for a 4-year college or any college education. And so starting out at a 2-year, what's called a community college or junior college, can make some financial sense. So you get the smaller courses, usually a smaller college, and you can be in and out in 2 years, and then you transfer over as a 3rd-year student to your 4-year university and complete your bachelor's program there. And so we gear ourselves to transfer to 4-year universities that are within maybe about a 100-mile radius of us. And there's about 1, 2, 3, I think there's 4, if I'm counting correctly, 4 colleges, 4 universities that we transfer to. But there's one that's really close by. There's one that's only about 10 miles away. And so I would say 75% of our students transfer to that one. And so we kind of gear our curriculum to them. We offer in the same 2 years what they offer in their first 2 years. So you can take the exact same courses through us, then transfer over as a third-year student. Which means once you get done with us, you dive into things like data structures, programming language theory, what else? Artificial intelligence, graphics programming, like the more advanced topics. Software development, and software development as a whole, right? That's actually their capstone course, is to, from beginning to end, work with a client and actually develop some kind of application for them, whether it be a website or a mobile app or a desktop app. Start from beginning to end and learn about version control and bug fixing and collaborating with others and collaborating with a client and changing the requirements, which happens all the time. And then by the end of your senior year, you've got this complete project that you've worked on that you can show in a portfolio. Oh, my in-class students are really lucky. I'd like to think so, but I haven't had any for 2 years. I haven't stepped foot on my college for 2 years. Actually, I've been there once or twice, right, to pick up stuff, but I've not actually been there for more than like 15 minutes at any given time. Are colleges changing their introduction to programming language to Python instead of C? Well, that's a good question. I have heard that a couple of years ago, we finally crossed a threshold where more than 50%, more than half of the universities had switched to Python instead of whatever they were using before. That means there's still about half of them holding out with whatever they were using before. For our transfer institutions, it's Java. Our primary transfer institution uses Java. So we still use Java as the introductory language. Personally, that would not be my preference, but that's where we are. Some other universities use C or C++ as their introductory language. Some use Scheme or Lisp or some dialect of that. And so it really puts us in kind of a tough position. Depending upon where you want to transfer to, you need to start with whatever language they expect you to start with. So most of our students will start with Java because our transfer institution expects that. But a few students need to start with C, or at least have learned C or C++ by the time they get done with us. So we actually have kind of 2 tracks through our curriculum. We got the track for our primary college, which teaches you Java, and then we got another track that starts you with Java, but then switches you over to C and C++. So by the end of your second year, you're pretty well versed in C++ and can switch over to them. I would have to say C would also not be my first choice for a programming language. Maybe C++. It can be a little simpler to deal with C++ in some cases. As to what would be my preferred first language, I mean, Python I think is okay. It has its rough edges, but there are good development environments for it, like the Python notebooks. I think those are pretty good. But Python's error messages in some cases are terrible. I would not recommend JavaScript as a first language, if only because the development environments of JavaScript just are awful. right? You run your JavaScript program in a web browser, and then you don't see the errors unless you look at the JavaScript console. And in some cases, the errors just produce like blank results, and so you can't see the results at all. And that's not a great start. In a very good curriculum, I think Scheme works pretty well. I've worked with that curriculum, and I really like it. So I guess these days I would have to pick maybe Python, maybe Scheme, and really, honestly, a lot of the old school programming languages like Pascal or what are some of the older school ones? Modula 2. I mean, those actually were designed to be teaching languages. And so there are some really good points to those as well. I mean, they're designed to be simple, give you the foundations, and then you move on from there. My own personal experience at university was we spent the first semester in Pascal, we learned that, and then immediately threw it away. Like, you've learned the fundamentals, now let's move on to something else. And so by the second semester, we were learning C. That's really how I think it ought to go, right? You learn one language, you reach the kind of the ceiling as to what you can do with that language from a practical point of view, and then you just throw it away and then apply those concepts to a new language that can take you a little bit further up the ladder. And then when you reach that ceiling, you throw that one away and you bring in another one. And the nice thing there is that by the time you've finished your 4-year degree, you've got maybe 2 or 3 or 4 programming languages that you know fairly well. As opposed to these days when you get to your 4-year degree and all you know is Java because you've used that during your entire 4 years. So I think that can be kind of limiting. And in fact, if I could be more honest, our actual progression was Pascal in the first trimester. We had three trimesters per year. So first Pascal in the first trimester, then we went into assembly language in our second trimester, and then C in our third one. So by the end of the first year, we knew Pascal, assembly language, and C. I think even some of the basics could be okay. For all its simplicity, old school 8-bit BASIC with those line numbers, and speaking specifically about the line numbers, which a lot of people find limiting, was actually, in retrospect, a good learning tool because it really reinforced the idea of sequencing, right? You do line number 1, then line number 2, then line number 3, then line number 4. And if you have a loop, you go back to a particular line number, so you really kind of can see the loops constructed in your program itself. You know, of course, these days people find the line numbers to be esoteric and kind of limiting, but it really kind of got the point across that there was the sequencing and looping and conditionals involved in executing your program. So I don't know. I wouldn't be opposed to seeing some of that come back somehow. And I know in your editor you number the lines, but the editor is really doing that so that someone can draw your attention to, say, line 5 of your program. Could we somehow integrate those line numbers into the actual program itself and reinforce that, like, lines 5 through 10 consist of a sequence of statements somehow, and that when you loop, you go back up to line number 5? Is there something we could do there? Maybe. Now there's always comments, right? Free BASIC has all the features of C or C++ with the clean, simple syntax of BASIC. It's a front end for GCC. So it gets compiled down into... So it's basically, you write this BASIC to C, there's a BASIC to C compiler, and then from there it goes into the C compiler. Hopefully you'll never see one of those error messages produced by the C compiler, because it should have produced a valid C program at that point. That was one of the things I didn't like about processing. You may have heard about that as a beginning language. Processing, which you can get from processing.org, is basically a front end for Java. So it's kind of like a simplified version of Java. But what you do there is it just takes your code and then wraps it up in the Java code needed to turn that into a valid Java program, and then passes it to the Java compiler. So it's not a proper compiler in that the processing front end doesn't do any kind of error checking on your program. It just simply puts in the Java code needed to turn it into a complete Java program, and then hands it right off to the Java compiler. And so what you see is Java error messages. And from a student's perspective, Java error messages are not that great, especially since they may mention things about your program that you've never heard about. As a processing student, you may only know about like loops and conditionals and methods, right? But they're not called methods because you don't have objects. They're just like functions or procedures. But the Java error messages may mention things that are not part of the processing language, but they're part of the Java language. And so that's a problem, I think. There really ought to be a processing to Java compiler that applies its own error checking and can produce appropriate error messages, so that by the time it gets to the Java compiler, you've got a syntactically valid Java program and you'll never see a Java error message. That would be the ideal thing. Saw some people on YouTube run a C program and then hack the code with Python by going into the executable. Huh. Well, I mean, that's always possible to do, right? So once you have compiled a C program, you've just got a bunch of machine code, and then you could write another program that would go and analyze that file and find the pieces of the code that you wanted and change it. So the executable file itself has a structure to it. It has like header information about like the name of the program and the size of the stack that it needs to allocate, the size of the heap, the size of the code segment, and then it has those individual pieces written in the file itself, along with a symbol table, which contains things like names of functions and variables and line numbers. And then you could go write a program to go in there, decode that file structure, and then change portions of it. That would certainly be possible to do. Going back, there's a comment here about the problem with Scheme is that it's so different from all the other languages. And that's true. Scheme is very different. But that can actually be a plus. You see, there are students coming into a university or college who already have some programming experience. So maybe they've done some Java or C or HTML or PHP. And there are students coming in that have had very limited experience. So you've got students who already have some experience. You've got students who don't have any experience. And that already puts those latter group of students at a disadvantage. So how do you help them? How do you help them kind of catch up to someone who has already had years of experience? And one solution there is to use a programming language that no one has ever seen before, so that everyone is equally confused. And so Scheme kind of acts as to use a colloquial term, a field leveling, right? Everyone's now playing on the same playing field, rather than some people playing at a more advanced level and some playing at a more beginning level. So there is some advantage, educational advantage, to using a language that no one has seen before. And so everyone has to learn it essentially from scratch. Because there's actually a huge problem in the computer science field with people who have experience kind of using that as a weapon against people who don't have experience. You know, they can be intimidating. They can put other people down. They can make them feel stupid. People aren't stupid. They just don't have as much experience, right? And so that's actually a huge problem in the computer science field of like the intimidation factor, and someone with no experience coming into a classroom, looking around and going, well, everyone else here seems to have experience and I don't. I don't fit in here. Maybe this is not the place for me. Maybe I should change my major. And that's not really the kind of environment that we want to foster. And so using a language that no one has seen before takes those people that have had experience already and puts them back at square one. So the people actually who don't have any experience now have a little bit of an advantage because they don't have any baggage to unlearn. Now, is Rust taking over for C or C++? I would say, based on what I've seen, C is still very firmly entrenched as a operating systems, embedded systems programming language. But Rust is gaining in popularity. It's certainly not as popular, anywhere near as popular as Rust is, as C is, but I'd say it's something worth learning. In that sense, maybe Scratch is good. You know, there are actually some universities that start you out on Scratch. You know, you don't do the full first term in Scratch. That you very quickly hit the ceiling in Scratch. But again, everyone's starting over from square one, and one of the nice things about having that ceiling is once you bump up against that, you start thinking like, man, there's got to be something better out there, and you can say like, well, there is. There's these other languages that have a very similar structure to Scratch, right? You still write kind of the same programs, but you type them instead of dragging and dropping. And so you can write much more complex programs more quickly if you can type them rather than dragging and dropping. I'd almost like to see, and maybe they're working on this, I haven't looked at Scratch in a while, I'd almost like to see like a textual version of Scratch, right? So you could drag and drop initially, but then when you were ready, you could just write the same programs but in an editor, you know, and then write them more quickly. And then you now have like a new ceiling that you can rise up to. So Rust is memory safe with a C-like syntax. It's a no-brainer replacement to C. Yeah, I mean, I'd agree with you there. Again, my experience with Rust is pretty limited, but one of my, I guess I have two hesitations to Rust as far as a beginning language. The first hesitation is Rust has its own standard library. It's not compatible with C's standard library. And what that means from a practical point of view is that when you compile a Rust program, it has to link in its standard library and cannot take advantage of the C standard library, which is standard on, you know, pretty much every computer system. So the executables that come out are not compact and small like for a C program. Like a C program, like a hello world C program is just a few hundred bytes of executable because the standard library gets linked in at runtime. But the file itself is pretty small. Whereas in Rust, when you compile that program, the standard library for Rust is linked in at compile time. And so you end up with this huge executable, multiple megabytes, because its runtime library has to be linked in at compile time. And to me, that just like, I don't know, it makes me feel uneasy, right? Because every executable is just this gigantic monstrosity. And of course, the counter argument to that is, well, disk space is cheap these days, so who cares, right? Or maybe the better solution is Rust standard library ought to be included with a distribution the way that C's standard library is, so that the programs can be linked at runtime rather than compile time. Yeah, so Akash is bringing up exactly the same thing. Is once the libraries are available everywhere, that'll get solved as Rust gets more popular, right? So, but right now that's kind of like a stumbling block for me. And the other thing is, Rust has a built-in package manager called Cargo, which is used to build Rust programs. And while I like that idea of having a built-in compilation manager, kind of like Make or Ant, I guess the problem is that in order to build Rust programs of even modest complexity, you have to use Cargo as a way to manage your program. And from a beginner's point of view, I would like to remove as few obstacles as possible. I would like to be able to have a beginner just jump right in, write a program, and compile it and run it and not have to worry about all this extra stuff. Is it possible to do? I think so, but again, I haven't used Rust enough to be able to make a honest opinion about that. But that's another thing that I kind of like don't like, is that you're sort of forced into using this compilation manager really soon. Like right after your first couple of programs, all the tutorials say like, okay, now start using Cargo to build your programs. And I like to teach in what's called just-in-time teaching, which means I'm only going to introduce a new concept to you when you're ready for it and when you kind of like have the mental capacity for it. And if you're still stumbling over like how to write loops and conditionals and declare variables and keep those things straight in your head, the last thing you need is another piece of the compilation process that you now have to learn, and that if you don't learn it, you can't get your programs to compile. So again, maybe I need more experience with Rust to be able to know whether that's really truly a problem or not. So there's some comments here. Cargo is not necessary, actually. You can use the Rust C compiler directly. I guess, I mean, I know that's true, right? Because your very first program, your Hello World program, doesn't use Cargo at all. It just uses the Rust C compiler. But if you follow tutorials on, if you're a beginner and you say like, man, I don't know how to write this program, I need some help, and you go and find some tutorials, if they all include this stuff about Cargo, you kind of don't know in your head what's important and what's not important. Do I need to use Cargo? I mean, what is it? Like, should I just blindly follow this tutorial that I found? Or, that's the problem I have, is if somebody goes out and seeks out additional information, is it all going to be wrapped up around this, inside of this Cargo stuff? Or can the beginning student be taught how to extract out just the piece that they need? Because a lot of beginners can't, in their head, separate the development environment from the language. They think that's all like the same thing. Like, I used to teach second semester Java programming. So I had students that would start with their first semester with some other teacher, and then they would come to me. And in my class, I used BlueJ as the development environment because it's simple, it gives good error messages, it has a little visualizer for data structures, really easy to use. But a lot of students came from JGrasp or Eclipse as their first development environment for Java. And so they would come to me, and I actually had some students say, I don't know how to write a program in BlueJ. I only know how to write a program in JGrasp. And it took a while for me to explain, like, it's the same Java programming language, it's just a different set of buttons you have to click on to run your program. But it really opened my eyes to this idea that some students can't separate the development environment from the language. They think it's the same thing. And so when they see a development environment that's different, they get stuck. And so that's my fear with Rust, is that they see this cargo thing and they can't separate that from Rust, the language. And they think it's part of the same thing. Okay, let me see if I can catch up here. So many programming languages nowadays, we need to keep learning them all. Yes and no. I mean, technology moves forward, and the languages you learn now will probably not be the languages that you will be using 20 or 30 years from now. If only because computing paradigms are changing. I, like most people, learned programming languages on single-threaded computers. Right? Your programs only use a single thread, and if you want to use more than one processing core, you kind of have to go out of your way to use those things. You have to bring in some library that handles threading and handles multiprocessing. We're starting to see some programming languages that make that easier to do, or make that kind of the default programming model rather than the exception. Python actually makes it pretty easy to do multi-threading. If you can wrap your program up inside of a function or a class, then you can just say, create a thread that runs this method, and then it just goes off and does it. Very easy. In C, harder to do. C++, harder to do. And I would avoid staying away from absolutes like Rust is the best or C is the best. There's always trade-offs. There's always pros and cons to everything. There can only be what's good enough for my purposes. What's suitable for what I need. It'd be no different than somebody saying hammers are the best. You don't need any tool other than a hammer. You know, you can cut wood with a hammer. You can assemble wood with a hammer. You can do plumbing with a hammer. You can do electrical work with a hammer. Sure. But it's difficult, right? So there are languages that are better at some things than others. Rust attempts to solve some of the memory problems that C has, so that can be good. It might mean you have to learn a bit of new syntax. My limited experience with Rust is that it's pretty close to C, but it's not exactly like C. There's some extra stuff in there. But turns out syntax is actually the easiest thing to learn. There's like syntax and then programming concepts. Syntax is easy compared to the programming concepts. Those are hard to learn. But initially, the beginning programmer just sees syntax. What do I think about Go? Oh, it's been years since I've looked at Go. I looked at Go when it like first came out. And wasn't it a Google project at the time? Well, it probably still is. And see, what was Go supposed to be geared towards? Wasn't it supposed to be like a JavaScript replacement at the time, which was like 10 years ago? Also, I think it was supposed to be kind of positioned where C was, like a language for doing system programming. So I don't quite remember why Go didn't quite catch on. But again, I took a look at Go back when it first came out. Did a few tutorials, kind of shrugged my shoulders and went, I don't see any real big advantage to this over some of the other ones that are currently in use, and so I kind of set it aside. Oh, Go is a bit slow. And again, reaching back into my brain, I think it's because Go, is Go compiled down to native code, or is it compiled to a bytecode, kind of like Java is, where then it's then executed by an interpreter, which is really going to make it sort of by default slower than C or C++. Oh, Go is compiled to native. Okay. So again, it's been years since I looked at Go, so I don't have really any good opinions on it. So here's a question for you. Is Go is it an open source language, or is it still kind of owned by Google, and Google primarily drives its development? I don't know the answer to that. Oh, it is open source. That's good. Supported by Google. All right, so it's kind of half and half. I mean, here's the thing. Like, if you have a language that's primarily supported by one company, then the progress on that language is really sort of at the mercy of that company. Do they want to throw extra engineers at problems, or do they want to preserve those resources for other areas of their company? And so by making it open source, it means that the developers outside of Google can contribute to it, which is good because it means that progress then is sort of independent of what Google wants to spend on it. But if it's primarily driven by Google or any other company, not just Google, but any other company, then its progress can be hindered by what that company wants out of that language and how much resources they're willing to spend on it. And maybe the question also is what problem space does Go try to address? Like, where is it kind of being positioned as? Is it being positioned as a language for embedded and operating systems programming? Is it being positioned as a language for web programming? Or as one that kind of sits in between the front end and back end, where like PHP and languages like that occupy? Maybe for parallel programming? So that can also be a limiting factor, of where the people who work on that language kind of want that language to be targeted at. So you're saying mostly for back-end stuff with easy parallel programming, not for embedded systems. So it looks like kind of being positioned where PHP occupies, right? That kind of middle in between the server's operating system and back end and presentation of data towards the front end. And then there's Rust, of course. this is kind of nice that Rust can work on a command line and you can compile down to WebAssembly. So in that respect, it could replace JavaScript. I think because Rust can compile down to WebAssembly, it also means that you can potentially learn Rust by just running it in a web browser, which is great for beginners because you don't have to compile, you don't have to install anything, there's nothing to maintain. There's no tool set you have to learn, like, here's your Visual Studio Code for editing, and then here's your command line for compiling, and here's something else for running it. It can all be like in a web browser, which is really nice. Oh, I was hoping I could actually run this. Can I run it? There, it says running. I don't know whether it's being sent to a backend, compiled, and then, well, I guess it is. Playground communication timeout. So does that mean it's sending it to a backend, the backend's compiling it, and then sending it to the, oh, there, it worked this time. It says hello world. These activities are clearly designed for someone who's already a programmer, not for someone who's just learning Rust as a first language. Sorry, I'm reaching into my bag here for oh, it's not gonna. I was getting a mouse out so I could use the mouse, but it's not going to work because the batteries are dead. Let's see. Oh, we can run this. Was I supposed to get an error with this? I don't know if that was supposed to be an error. Oh, here, fix the 2 issues so that it runs without error. Oh, I see. There's a couple of places where it says, fix me. Got it. All right. I have the biggest hopes for Rust. Maybe Go has some hope if it can replace Java. Java is my most hated language. And then Nunio says, why do you hate Java? And for me personally, I always look at a programming language from the eyes of somebody who's just starting out, who's just learning to program. And so, I can't say that I hate Java, but I don't think it's a good first language because it's really difficult in Java to write that first program. There's like 20 things that you have to get exactly correct or it just won't work. And 20 things that are kind of unexplainable to a beginner, to someone who's never programmed before. And so some programmers, some beginners say, like, what is all this stuff about class and public and static and void? What is all that stuff? And you just kind of have to say, I'll tell you later. I can't explain it now. And for some beginners, they go, oh, okay, whatever. And they kind of keep it in the back of their mind that those gaps in their knowledge will be filled in. And then some other people just really get stuck on that. They say, if I don't understand everything that I see on the screen here, I can't move forward. And I think for the beginner, that's where Java kind of falls flat, because you can't, as a teacher, explain what static is and public and class and why you would want to replace those words with other things until they've had much more experience. And in fact, you probably can't even explain what static is until, like, 2 or 3 months into your learning. Which I think causes a problem for beginners. So it'd be nice maybe if there was, I don't know, Java Lite, which I guess is sort of like processing, right? That does away with all of that extra stuff, allows you to dive into writing your first programs without all that stuff needed to make it work. Maybe processing would be better if it didn't just simply hand it off to the Java compiler, if it had its own compiler. And you're right, Java programs tend to be quite verbose because all you've got are your primitive operations and everything else has to be a method. That's why I thought C++ could be better in some cases, because the operator overloading lets those operators like plus and times do what you expect them to do, but on more complex data types. Like, you can overload plus for strings to mean concatenate, which it does in most programming languages, but you could also overload times to mean like repetition, like take the string and repeat it 2 times, for example. You could have a library to make arbitrarily large integers, usually called big integer. And in Java, if you want to use the big integer library, everything has to be turned into methods. So if you just want to add 2 numbers together, you have to, first of all, you have to create those 2 numbers using new, and then you have to call the add method in order to add them together, and then put them into yet another big integer object. So it just gets really convoluted and verbose. Whereas in C++, you could overload the plus operator, and it will just work like you expect it to do. I think that's kind of nice. On the other hand, the operator overloading can get out of control. The whole like C out and then the 2 less than signs. Whoever invented that was clearly not thinking about the beginner, right? Because that's like the only place in the whole language where you see those less than signs used to mean like send data from here to here. You don't see that in any other part of the language. It's like only used for file input and output. And it's almost like we're just showing off at this point that we can use these operators, which used to be used for bit shifting, and use them instead for like data redirection. So I kind of think that since those operators have been there since day 1 in C++, that they were just showing off. There's like, hey, we can do this. This is kind of cool, right? But to me, it's ridiculous. Why can't I use the less thans to assign variables? Why can't I go like x less than 5, right? And put the value 5 into x, right? You can't do that. So Java's never really appealed to me. It seems to take the worst downsides of compiled and dynamic languages and mix them together. So I never learned that, but I like the C-like syntax. Yeah, if I'm going to write a C-like program, I'm not going to choose Java as my first one. I'm going to use C or C++ or Perl. I really like Perl. That was one of my first languages after C. But I suppose if I have to write a quickie application that uses buttons and menus, I'll probably use Java. It's easy enough for that. Anyway, I think probably enough chatting for now. There's a question here about explaining scope of variables in C, and it might be better to wait for our C programming class to talk about that. C, C++, Python are my favorites, and now Rust. Honestly, I never really got into Python either. It was good for some stuff, but as a former Perl programmer, I found some of Python's limitations to be like deal breakers. Things that Perl would do that Rust refused to do was just like, well, I'm perfectly capable in Perl. Why would I want to use Python? So I never really got into it because it seemed to me like Python and Perl kind of positioned themselves in the same space, and Python just was harder for me to use than Perl was. So I never really got into it. But on the other hand, I do like Python's treatment of parallelism. It's really easy to do that in Python, so there is that. And Python 3 has a much richer set of data types than Perl does, and so pluses and minuses for each one of them. Will we ever see an operating system built with Python? Unlikely. Python runs isn't interpreted. Most Pythons are interpreted, so you really don't want your operating system to be interpreted. The nice thing about the Python library is you can just say, take this method and run it in a separate thread, and whether that's run on a separate processor or a separate process or a separate thread is really up to the runtime environment, and you as the programmer don't have to worry about that. And that can be extended further to things like GPU programming, where you can say, take this method and run it on a thread, and if it wants to send that over to the GPU, that's fine. You don't have to worry about different styles of programming depending upon how you want the multi-threading to be done. What's a thread? A thread is like it's like a separate process, a separate program, but it shares the same memory space. So threads could share variables, whereas separate programs can't share variables. So you could take two functions and run two blocks of code, basically, and run them on separate processors simultaneously, but you could share data between them. So whereas spawning off a new process is a fairly computationally expensive thing to do, creating a new thread is usually very easy because you don't have to set up a separate memory space. All you have to do is set up a new processing space. Well, I think it's 12 o'clock now here, so I think we're done. It was great chatting with you. I like talking about pluses and minuses of programming languages because there are no absolutes, there's always just trade-offs. And there's really kind of only opinions. Like, I like this because, and I don't like this because, rather than absolutes. Like, this is awful and this is great. right? This is awful, it will always be awful, and this is great, it will always be great. Because programming languages are positioned into use cases. So not all programming languages are useful for all use cases. Could I make a video about concurrency? Well, think about it. But primarily I'm making videos for the specific contents in my courses. So that's my primary objective. So anyway, let's wrap this up. I hope that you all have a great rest of the day. For some of you, it's nighttime, so go get some rest. And then we will come back on Thursday, tomorrow, for my C programming course, where we will continue learning how to build data structures with arrays and structs, and learning how to sort and search them efficiently so that we can crack MD5 hashes really fast. All right, so take care, you all. Be safe, be happy. Talk to you later. Bye-bye.